Okay, hello. Alright, so today we're going to start compressible flow notes and lectures. So there's some problems on the final that involve this concepts, and there's no homework assigned, but hopefully you still watch and listen because, the concepts are on, PE exams and other things like that. Okay, so everything we've done up until this point Okay, so everything until now has been incompressible. What does that mean? That's just saying that the density is some constant value. But now we're at the point where we're going to now relax that assumption, and this is the concept, right, of compressible flow. What does that mean? Well, simply sort of just this. Right, just alone from just Navier-Stokes equations and other simplifications, you can't make this assumption. So you're kind of splitting flow into two cases. Either it's a constant value or it's not a constant value. So it's a binary relationship. So, okay. What does that really do to flow since we've studied it up until now? Okay. Well, before we answer that, there's just a couple things of when is something compressible? Flow is a good thing to ask. So a couple sort of thing is, right, if you're fluid, and none of this is mathematical or rigorous right now, but just intuitively, if the fluid's a gas, you're going to have compressibility issues. We'll see why that is later, but that clues you into, I have a compressible flow problem. Sometimes it's even called right? Some compressible flow books are actually just called gas dynamics for this reason, that it's usually you're working with a gas, so you have compressibility issues. Not the only thing though, right? You could actually just have very high temperatures. Also could get compressibility effects if you're in this extremely hot regime. We don't really deal with that in this class, but that's just because of a thermodynamic thing that we'll see later. You could also have kind of related to this, where just right, if you have enormous pressures, you could even have some compressibility effects. If you take water and you're flowing it with just a dumb degree of pressure, you could get some compressibility effects in your flow. But you don't normally see that just because of the I think if you raise by 800 atmospheres or something, it's only a compressibility effect of 5%. So you don't even really need to worry about that, but it's possible. And then kind of it's in terms of speed, and that's kind of where we'll really get in, right? If your Mach number is kind of around order 1, where Mach number is velocity, speed of sound, or speed of the medium. If this number starts to approach, right, sort of around 1 and not just super, super small, you're going to get compressibility effects. This is essentially next lecture, but right now we'll just go into sort of why these are reasons for your flow to be compressible. And we'll do it we'll do it from physics, but that is all very intuitive. I think everyone would understand that if it was a gas, there'd be compressibility issues, but we can think of things a little bit more. How do we handle these problems? Well, just like we did with our compressors, we could just lay out the fundamental framework is that you have some coordinate system that you draw, right, like this. You have Newton's coordinate system, and you have, right, another blob of fluid that we draw. Okay, so this is a boundary. This is some region of fluid, right? Or volume. Okay. And, right, for your volume of fluid, here's a point in my region of fluid, so I have sort of an X naught, Y naught, Z naught inside of it, right? Right, before we had these fields we were talking about, where we had what was the velocity vector field, right? So this was a function of x, y, z, and of t. But the other thing now is, since rho is not constant, that's also now a field. So this as well, in the very rigorous dynamical equations, now the density itself is a scalar field in the fluid region. So that's the biggest change. Before, this was just a constant value, so any derivative of quantities just turned out to be zero. But if you relax that compressibility issue, now this is a field, and then we would still have our other scalar pressure field, right? So compressibility introduces this extra field we have to track of all the little differential little cubes of liquid or gas now. So that's right. So immediately, that's the biggest thing that changed in all the little differential boxes of fluid we had. I'm not going to go through all those steps, just like we did sometimes the shear of these boxes. But this has an effect because now you can't factor you can't factor this changing density field out of any of your control volumes for little boxes of fluid. But in the end, after you do all that stuff, you get another set of governing equations. And I'm just going to write out kind of the point of them. Remember the material derivative or the substantial derivative? That was lecture 1. So remember, that's what I mean with this capital D operator. So maybe return and look over that. But right, you end up getting just this sort of, I wrote it like this, just because I want to. And now, again, material derivative of it. Okay, so I had function of V. This is the function of V. Right. Same with this. So now with compressible, this is the sort of the new Navier-Stokes equations. Is you have the velocity, right? So this is conservation of momentum. Looks like this. Conservation of mass. And this one right here is a sort of extra because we just had these two things before, but this is really, right, this is a conservation of your energy, you could think of it. So I sort of actually remember this as the thermo equation. And we'll get into why it's a thermo equation in a bit, but right, this is sort of your thermo relationship here. You still have nonlinearities because this means that every point of velocity, density, and pressure are related to the points that they are already. So that's just an issue of complex states like that. But that's, you don't have to even look at these terms, but really the fact that this appears is what's troublesome for compressible flows. Right? Before you could factor out this, and then you had, right? Remember before you could just do this. This is a constant value. So really what happened in your mass conservation equations, you could just say that I have a divergence-free vector field for velocity, blah, blah, blah. But the fact that you could factor this density out because it was a constant was important. You can't do that anymore because it's a field, and it makes things just a lot harder. So you get more equations, right? More hard differential equations that will never be solved. Sort of the techniques, though, for what we have of doing compressible flow, I also kind of want to say what we do is really we go from state 1, at least in this class, right, to a state 2. So this is equilibrium states of fluid, and this is what we call, right, a process, right, sort of dynamical. So it's dynamical, it's anything, sort of like through a tube. But then, so here, sort of my region at time 1, and then my region 1, and then my region at time 2. Well, these are equilibrium states. So we don't even deal in the undergrad stuff of like the actual differential time evolution of compressible flow. We just look at the two states occurring. And this is very similar to like, you have a tank of water and you're going from point A to point B. So moving fluid from point A to point B, kind of the same thing. So we're getting the same energy equations of how do I get my gas in state A to gas in state B. Okay. Forewarning, so I thought this was interesting to say, usually in the textbook we have, before I get into all this stuff, in the textbook, we've had an average, right? So for every chapter, the average equation summary in the back of your chapter, I calculated this, it was about 8 equations in the back of every chapter in the text that we work on. So there's a little summary sheet with equations you go over, and it was always around 8. For this section, if you look into your book, right, it jumped up to 43. So there are a ton more equations for compressible flow if you just look at the back of your summary sheet. So while there were a lot, there's reasons why you need 3 times or 4 times as many, because you have to prescribe these 3 different states all the time. So before you get afraid that there are just so many more equations, they're all saying the exact same thing, right? They're relating state A to state B. But you have to do it for pressure, temperature, and density. So you have kind of 3 equations for every 1 equation you would have in the incompressible flow. Okay, so let me just, again, I think I wrote them out. Let me write out actually the other terms. Right, so if we had incompressible, and this will be compressible. I for incompressible was incompressible. So, right, the governing equations we had before was, right, continuity equation. Well, this is mass conservation. And then this is the other one we had. This is the vector, gradient of pressure. This is vector. Body forces. So these were the incompressible Navier-Stokes equations. Right? So this is sort of one equation, and that's a vector equation, right? So we have 3, this is representing 3 different equations. So, right, and that closes the system. Because we are trying to figure out U, V, W, and our pressure field. So here are my 4 unknowns, and I have 4 equations. So that's the closed system right there. For the compressible, we end up getting, here's this material derivative of the density. So now your mass conservation becomes this. Okay. And then the momentum equation, I'm going to have to take up more terms here. Okay. This is the same. You still have this viscous dissipation term, but you have this extra term. I use a lambda, and this is a gradient of vector field. So this is another sort of dissipation term, but it's a dissipation due to the compressibility of the flow. So lambda is sort of it's a second viscosity. It's related to mu. It doesn't really matter. It's a scalar term. Fact is, this was 0 before based on this equation, so that term went out. And then we also have our body forces, which usually are just never there, but if you had magnetic or electrical forces, those could be present. And then the problem is now, okay, so this is one equation here, still 3 equations here, but now I don't know, right? I need to find my unknowns for compressible, right? I need to find this field, U, V, W, right? And I still need to find the pressure. So now that the density became an unknown, I don't have enough equations to solve the system because I only have 1 for the density. This gives me 3 equations, but I need another one if I want to set what this pressure field will be as well. And that's where this dynamical, this is from von Mises, does this. People do it all different ways, but you just need another one. So here's one I like. These B's and A's are thermodynamical quantities, which we'll get into, but this is sort of the point of compressible flow, is you have to add this extra equation because that's the only way you can actually solve for the pressure as well. So where did this equation come from? is the biggest thing. So this is related sort of with these quantities and these quantities. We'll get into it. But this is from, right? This is about your equation of state that's talking about density. So this is from thermo, right? That is where you have to go to figure out some physical reason for what this evolution equation is going to be. We need something called an equation of state. That is relating all these things. So this first one is going to mostly just be, let's dig into thermodynamics to talk about pressures, densities, and now temperatures. And actually these B's and A's are actually involved in temperatures. We'll never go back to this, but I just kind of always like looking at the full governing system to get a sense of what do I need to do. Looking at it this way, you can clearly see that you have to have some other equation to close your system if you want to solve anything, computer or no computer. But that's why we're mostly going to have a bunch of thermo talk for this, because we want to understand how this equation of state relates to my pressures, my temperatures, and my densities, right? Now, if the equation of state does not sound familiar to you, I promise you it is, though, right? Because here's a very simple equation of state. Remember from chemistry, this is an equation of state, right? You could solve for what density is, right? And you could actually have that pressure, you just divide rho r t. So what is this doing, right? This is some equation that, right, is relating. You could have my density as a function of pressure and temperature. It's a pretty simple equation, but still an equation, right? And there are all kinds of more complicated ones of these. In fact, right, in general, the equation of state can be written as just some function that takes pressure, temperature, and density 0, right? It could be, right, and you can see this from just the top one right here, right? You could just have right, so then you have pressure minus, so then this would be your function or the equation of state. So that's one equation of state. It's the only one we're really going to use, but we need it to talk about how the densities and the pressures and the densities, pressures, and temperatures are related to each other. Okay. So that is where we're going to go now. Next is, right, talking about the thermodynamics of these things. And essentially, right, we're just going to use the implications of this equation of state, right? It's the ideal gas law. Sometimes called perfect gas law. But that's the point. So we're going to use the actual thing like this, but we have to talk about the thermodynamics and all the first laws and second laws and things like that to see what are the implications of having an ideal gas law with respect to compressibility and respect to other things. We even actually can go into this ideal gas law and derive right? That's the end. The last part of this lecture will actually be using thermodynamic quantities with ideal gas laws to get a speed of sound based only on the thermodynamic quantities. And that helps us to find Mach numbers. So that's where we're headed. Let's get into it.